joining the meeting also. Let me just say welcome, everyone, and then we're going to start with the meeting. Hein will be doing the training. Just a few things. If you've got any questions, you can just write all your questions in the comment section. And Hein also prefers that you ask questions at the end, but at least if you write them in the comment section, we can be able to address them also at the end. And thank you for joining us this morning and enjoy the training. Hein, over to you, sir.
Thank you, Tebogo. Good morning, everyone, and thank you for joining today's training session as well. Those of you, that's the first time, my name is Hein and I'm an electrical engineer. A bit of background about me, I studied at University of Pretoria, afterwards did my postgraduate studies at University of Stellenbosch, specifically in the field of power quality and renewable energy. And I'm excited today to present to you on voltage waveform quality assessment. This is part of a 3 series that we've been doing the last few months. The first session was on power quality standards, second one was on voltage dips, and now the last one in this series will be on voltage waveform quality assessment. I'm just going to share my screen and the presentation. If you have any questions, as the Tebogo said, please, you can write it down, or we will have a few minutes afterwards to take your questions. All right, enjoy the session. Thank you, guys. Okay, Tebogo, can you please confirm if you can see my screen?
Yes, I can.
All right, thank you very much. All right, so as I said already, today's session will be on voltage waveform quality. Specifically, the content that we'll cover today is we'll look at a few specific parameters or a few things that needs to be assessed as part of the NRS 048 standards as voltage quality. One of them is voltage regulation, voltage unbalance, then your voltage total harmonic distortion and individual harmonic components, and then lastly we'll cover voltage flicker as well. So this is the first leg of which falls under the quality of supply banner. As I said, we already covered disturbances, which are voltage dips, swells, and transients. And today the focus will be on quality of a waveform. So how do you define the quality of a voltage waveform? Using specific parameters such as the voltage magnitude, unbalanced, harmonics, and flicker. Now, the NRS 048 Part 2 is the standard that we'll mostly be referring to in the training today. That's the standard that we use in South Africa that is used to or defines the compatibility levels or limits that's being used to compare your voltage quality with the limits that's defined in that standard. So firstly, let's look at voltage magnitude or voltage regulation. The definition for voltage regulation from the NRS 048 directly quoted is the ability of the steady state RMS voltage to remain between the upper and lower limits that are defined in the NRS 048, and we'll look at that in more detail as well. Now, utilities supply voltages that are not perfectly sinusoidal or not perfectly or perfect symmetrical. So they're not perfect in magnitude and phase. Additional to that, users, customers, further decrease voltage quality by drawing a nonlinear currents through non-zero supply impedances, and this causes upstream voltage drops resulting in, or which can result in poorly regulated voltage magnitude. Withdrawing harmonic currents cause harmonic distortion of voltage waveform, and due to asymmetrical supply impedances or unbalanced load currents can cause voltage unbalance. And we'll look at that in a bit further on in the presentation. Now, voltage regulation is the long-term regulation of the voltage established through transformer impedance and a tap changer. Tap changers are not everywhere and also not well maintained. And what also plays a big impact on your voltage regulation is the fault levels at the point of measurement. And that's normally a compromise between investment and performance. So what do I mean with fault levels? On a system with a high fault level, you normally have a lower impedance, and vice versa, a lower fault level will have a higher impedance. So a current that's being drawn over an impedance, the larger that impedance is, the bigger will be the voltage drop and the bigger impact it can have on your voltage regulation. So regulation will decrease with loading that increases over time and will also be impacted with a lack of planning and upgrades. Long lines and loaded transformers cause a variation in voltage magnitude. All right, so that's just the introduction on what can impact your voltage regulation. The IEC 61000-4-30 specify the recording of 10-minute RMS voltages for assessment. So if you need some more information on how voltage magnitude and RMS voltages are calculated and measured, that is defined in the IEC 61000-4-30 for that definitions. Okay, so just a few concepts on voltage regulation before we look into the standard is what is nominal voltage? Nominal voltage are voltage for which the system was designed and equipment specified. Now, also the declared voltage is then the voltage at which a system is operated, taking into account the local network conditions. It could be operated at a higher voltage than the nominal. And this is normally specified in the supply agreement. So the first thing that's important for a voltage assessment is that your voltages are assessed compared to the declared voltage and not your nominal voltage. So if you look at this table 1 that is copied from the NRS 048, you'll see that at all the nominal voltage levels, so we have 44 kV, MV, which are 11, 22 kV, all of the voltage levels on NV and up compares your RMS voltage to the declared voltage, which are sometimes or mostly supplied or specified in your supply agreement. On LV, it's a bit different. On LV, we compare voltage compared to the nominal voltage and not the declared voltage. So that's why it's important when you set up a power quality recorder and you set up a measurement point for recording, that the declared voltage is correctly defined. And so that when you compare your voltage regulation on different meter points or at different measurement points, you can compare the values with each other because it's the same, you set it for the same declared voltage. Now, also a difference between MV and up and LV is that your voltage RMS or your voltage magnitude for assessment uses the 95th percentile and 99th percentile values. For MV and up, the 95th percentile values are compared with a -5 and +5% lower and upper limit. So if you define your declared voltage to be on 11 kV, your 95th percentile voltage or your RMS needs to be below -5 and +5 of that declared voltage for 95% of the time. And then for 99% of the time, your voltage RMS needs to be above and below -10% of the declared and +10% of declared. So there's a range that you need to operate within to comply to the voltage regulation. On LV, your 95th percentile is compared with -10 and plus 10%. Or on the lower one is compared to the minus 10% and not 5% as for MV and up. That's the main differences on that. So if you set it up on your system, just make sure you set the declared voltage up correctly and the nominal on LV. Okay, so the compatibility levels that's on this table defines the maximum and minimum levels that we already mentioned. From 2015, version 2015 of the NRS 048, a 7-day sliding assessment value are compared to the compatibility limits. So your 95th percentile value or your voltage RMS for 95% of the time in a 7-day window is compared to your limits that's defined in this table. And those 7 days window changes every day. So it's a continual assessment value that's being compared, and I'll show you an example of how that looks on the next slide as well. Yeah, so that's basically how that works. So here's an example of intermittent voltage regulation. This is an example of a measurement point where the 95th percentile upper value or maximum value is exceeding the 105% limit. So again, as we said, the 95th percentile 10-minute RMS voltages needs to be between 95 and 105% of your declared. And in this case, we can clearly see, looking at this green bars that defines the minimum and maximum 95th percentile value, that value is above 105%, the 105% limit, and therefore not complying. So for this period, the maximum value was measured as 106.1. Bradley, I see a hand.
I'm not able to see the screen.
So are the rest of you also having issues seeing the screen?
We can see the screen. I think, Bradley, your camera is on. Can you maybe switch off your camera? Maybe you will see the screen. Yeah, it's off now. Can you see the screen?
Nah, I still can't see it.
Okay, can you maybe leave the meeting and come back, and then let's try it that way.
Okay.
Thanks, Bradley. Sorry for that. Let's just maybe give it a second for Bradley to join or rejoin.
Can you see the screen now, Bradley?
Unfortunately, I can't.
Okay.
All right, Bradley, I'm not sure where the issue might be. If no one else is having the same issue.
Sorry, Peter here. For City of Cape Town, people won't be able to see the screen, unfortunately. I've had that all the time as well. I haven't figured out exactly why. I think there is a way to bypass our City of Cape Town server. I don't know, Henko, is Henko on board today? Henko, look, Bradley, we will get back to you. We'll sort that out somehow. For now, you just won't see anything for now.
Okay, it's fine.
Yeah, our apologies for that. What we will do is we are recording the session, so we will share the recording afterwards, or it will actually be uploaded to our YouTube channel that you'll be able to get the video recording afterwards. Our apologies for that. All right, just to continue where we left off. So this is just an example of the intermittent voltage regulation. What we can see here, at this specific point where we're measuring is that the voltage regulation are quite stable in a stable band, but the voltage regulation is high. So it's exceeding, on the upper value, it's exceeding the 105% limit for 95% of the time. On the next slide is an example of a point where there's a good voltage regulation. In this case, we can see that for all four the limits, for the 99th percentile and 95th percentile highest and lowest values, that all of them are complying, that's within the limits, and that if we look at the 7-day sliding assessment graph, we can see that the voltage regulation is quite stable and that the average runs on 100% of the declared. So the supply, you can also see that the band between the minimum and maximum is also not as large as at the previous measurement point. So this is all copied from a power quality assessment report generated on our OSPREY Pro or VECTO Grid OS system, which I will also show you an example of in the end of the session. Right, so that is how your voltage regulation is assessed and how you can compare your voltage regulation with the limits. Next, we have voltage unbalance. So the NRS 048 defines voltage unbalance as the condition in a polyphase system in which the RMS values of the line or phase voltages of the fundamental component or the phase angles between the consecutive line voltages are not equal. So in an ideal three-phase power system, your phase voltage will be exactly the same magnitude, and they will be displaced 120 degrees out of phase. Now, voltage unbalance is a value that's expressed as a percentage of your negative sequence voltage divided by your positive sequence voltage. That is how voltage unbalance is calculated and defined. Where or what causes voltage unbalance? So large single-phase loads on a three-phase network will lead to voltage unbalance. Unbalanced three-phase loads, or for example, a blown fuse in one phase of a three-phase capacitor bank can also lead to voltage unbalance. All right, for the compatibility or the assessment of voltage unbalance, a compatibility level is set and is defined in the NRS 048 Part 2. And it's not a limit, it's a compatibility level. And the compatibility level is 2%. So your voltage unbalance, your 10-minute aggregate voltage unbalance value, expressed as a percentage, needs to be below 2% for 95% of the time. That is the assessment criteria. Okay, so what is bad about voltage unbalance? If we look at an example of induction motors, so heating in induction motors due to additional losses. So if we look at rotating loads, motors, they produce less torque and operate at a higher temperature. So unbalance breaks down the rotating load, torque production reduced due to the opposing negative sequence torque. This causes the negative sequence current of the motor to increase, and this leads to operating temperature that increase, also increased losses, and therefore the insulation strength degrades faster due to the higher operating temperature and can result in a motor that fails earlier. This is just an example of what voltage unbalance can lead to and what's the effect and impact of voltage unbalance. It can also affect thyristor converters and the synchronization in VSDs, increase your apparent power or your reactive power component, leading to a reduced power factor and increased line losses. Okay, an example of voltage unbalance. There we have a nice arc furnace as a load, an image of that. That load draws a very unbalanced current, as you can see on the waveform. And unbalanced load like that will result in unbalanced voltage, as you can see on the bottom graph on the page as well. So arc furnaces are one example of a load that are common in causing a high voltage unbalance. Another example here we have the voltage unbalance being plotted in as this time. We can see, or actually the RMS voltages, we can see the difference in the three phases, in the red, white, and blue phase. We can see the difference in magnitude between the three phases. If we look at the histogram graph that you'll also be able to get from the report that's generated on Osprey Pro, is that if we look at the histogram for the red phase, we can see that for most of the time, the distribution of your red phase is running at 96%. So it's running well below 100% of the declared. So this is all in relative to your declared voltage. The green phase is on average running close to 100% of the declared, and your blue phase is running high. So you can see the difference in that. And if we look at the 7-day sliding value, we will see the scale is not that nice on this graph, but we can see that this is the limit, the 2% limit, and your 95th percentile value, which is the green graph, is now cut off here, but it is well above that 2% level for the period that we're looking at. And here's just a longer assessment over time for a longer period. So you can see there's periods of time where your voltage unbalance values were higher than other times. Specifically here in the middle, you can see your green graph, which is the 95% of voltage unbalance value, is above your 2% limit. Okay, now next we have harmonic emissions, or we'll be looking at voltage THD and individual voltage harmonics. So firstly, what is harmonic emissions? Harmonics are synthetic components in the frequency domain, which helps us understand the time domain waveform distortion. So the majority of harmonic components exist at integer multiples of the fundamental frequency, which in South Africa is 50 Hertz. And normally the waveform distortion is expressed in THD, or your total harmonic distortion, as a percentage, which is a measure of the effective value of the harmonic components of a distorted waveform. So it provides you with a good indication of how distorted your waveform, your voltage waveform is by using your THD. But it's important to note that THD only relates to the contribution of harmonics up to the 50th harmonic component. So that's up to 2.5 kilohertz and not above. So that's an important thing to note. In the modern power system and where we're heading, it's becoming more common that there's also an increase in higher harmonics above the 50th harmonic caused by inverters that switch at higher frequencies. So that's where it becomes important, and where the standard lacks is the assessment and the investigation of higher harmonics. It's not at this stage being assessed from the NRS, but it is something that will impact or needs to be investigated as well. So THD is one parameter that's assessed, but also your individual harmonic components also needs to be considered separately. So there's also limits being specified for individual harmonic components up to the 50th harmonic, depending on your voltage level. All right, so nonlinear loads distort the current, and the distorted current, let's start by what causes voltage harmonics. A nonlinear load distorts the current, and the distorted current passes through a system impedance, which creates a harmonic voltage drop at the various frequencies. The harmonic voltage then appears at the load pass bar as a voltage distortion. Just to show you a simplified schematic of that, very simplified, we have a perfect sinusoidal supply voltage with impedance, a line impedance, and then a nonlinear load. This load draws a nonlinear current through the system impedance or the line impedance. That causes a harmonic voltage or voltage drop at harmonic frequencies, as you can see over the impedance, and that will lead to a distorted voltage waveform on at the load bus bar. So that is just a short explanation of how voltage harmonics are introduced or introduced or generated. Here's an example of a load on an LV drawing distorted currents. You can see it looks like 6 pulse rectifiers, and an example of how that load currents affects your line voltages on the point of measurement on LV. So we can see how distorted the waveform becomes. Okay, so how is voltage THD measured? Firstly, it's defined or specified in the IEC 61000-4-30, which specify how voltage THD is measured. Time domain voltage can be written as harmonic phasors. So for each phasor, your harmonic will have a magnitude, an RMS magnitude, as well as a phase angle. And your THD are then calculated every 200 milliseconds from the harmonic phasors. So using the magnitude and angle, and it's calculated using this formula. So it's the square of your individual voltage phasors up to the 50th harmonic, and then the square root or the sum of that, and then the square root of that divided by your fundamental voltage. So that's how THD or voltage THD is calculated. And it's aggregated from 200 milliseconds. So that 200 millisecond voltage THD are then aggregated to 3 seconds and 10-minute values, which are then used for your assessment. So the 10-minute values are compared to the compatibility levels, which are specified in the NRS 048-2. Yeah, so Randolph, we have a question here from one of my colleagues. Randolph, yes.
So, Hein, just a thing to note here, your third bullet where you say harmonic phases have RMS magnitude and phase angle. Just look at the formula as well for our audience. The THD formula only considers the voltage magnitude and not the phase angle. So although THD is a useful measure to compare against, it really only boils down and summarizes the magnitude side of it, showing you half of the picture.
Cool, thanks, Ronald. So, so if you then have an example or case where your THD voltage is 0, that then means, or in concept means, that the waveform doesn't contain any harmonics up to 2.5 kilohertz. Now, practically, you will never see that, but that is the ideal case. But it doesn't mean there isn't harmonics above 2.5 kilohertz. So just take note of that. And this is something that we have seen from our experience that is very important in the distributed generation, where the THD is used as a value to spec your equipment, like the transformers, and they do not define, or the inverter manufacturers do not define the higher harmonics, which also needs to be taken into account when designing and speccing, for example, the transformer. So it's very important to just take note of that. So the compatibility level in the NRS 048 for networks or power systems below 33 kV is 8%, and For above 33 kV, it's 4%. Okay, now in addition to the voltage THD, you also need to assess your individual voltage harmonics, and there's also compatibility levels specified for each individual voltage harmonic. And that is specified, or voltage harmonics, individual voltage harmonics are calculated as a percentage of the fundamental harmonic, fundamental component. And it's again, the compliance is required for 95% of the time using the 10-minute values. So that's again the criteria using the 10-minute individual voltage harmonics, and you compare that to the limits for 95% of the time, the value that's for 95% of the time. A site can be compliant to THD, but uncompliant for individual harmonic components. All right, so just a few examples of characteristics from specific loads. A 6-pulse rectifier, for example, it normally generates the 5th, 7th, 11th, 13th, 17th, 19th, 21st, and 23rd harmonic components. So here's the formula you can use to, so it's 6 n plus minus 1. So the first 2 harmonics you can expect at the 5th and 7th harmonic. And then similarly, you can use this formula to calculate what harmonics are normally generated by 12-pulse rectifiers. That's the 11th, 13th, 21st, and 23rd. So just an example of assessment of voltage THD. In this case, we have a measurement point where we are doing an assessment over a month period. The assessed value, so the highest 95th percentile 10-minute voltage THD value in this period was measured as 2.5%, and that compared to 8%, you can see it's complying. It complies to the standard, and this is just a sliding graph that shows you how the voltage THD changes over this month period. The red graph being the maximum value, so the maximum voltage THD, and the green graph being the THD for the maximum 95% of the time value. And then you have your average, which is the blue graph. The bottom graph here that you also get from our report that you can generate automatically shows you for in this month period, how does your voltage THD looks in a typical week. What you can see here is how the THD decreases during the day, but actually increases during the nights. And this is something that you can commonly expect from or by points where there's industrial loads, because large industrial loads normally during the day lead or cause or have damping. So that damping will then actually lower your THD, leading to then higher values during the night when the damping on the network is lower. Okay, then in the NRS 048 table 4 and table 6 define the limits, the compatibility or levels for individual voltage harmonics. The table 4 defines the levels for LV and MV networks, and table 6 for HV and extra high voltage networks. You can see that there is limits for your odd harmonics and also your even harmonics. And then at high voltage and extra high voltage, it's only for certain odd harmonics where there's limits being specified. And this is all as a percentage of your fundamental voltage. Okay, here's an example of an assessment of the individual voltage harmonics. So we have the table that compares for a certain period that the assessment is done for this month. We compare your specific individual harmonics, the assessed value, with the levels that's specified in our NRS 048, and then provide you with the result. This is again all automatically generated for you using our Osprey Pro reporting functionality. And it also gives you a harmonic spectrum plot that compares your assessed value, that's the red, to the limits. You can see at this site, it's all well below the limits and complying to the NRS 048 limits. All right, and then lastly, that also needs to be looked at for voltage waveform assessment is your voltage flicker. Voltage flicker is the periodic fluctuation of voltage amplitude that results in the flicker of lighting, particularly in incandescent and LED lighting. This flicker, that is a physical phenomenon that you can see or sometimes see, can affect humans, will affect people because there's a change in lumen production, normally close to around 8.8 hertz, which can lead to headaches, eye irritation, etc. So I'm not sure if you've seen examples of that. If you get headaches in the end of the day, maybe you have a case of voltage flicker. Yes.
So just a note on voltage flicker. This is a phenomenon caused by the input voltage to the equipment. Not to be confused with the flicker that could happen on LED driver failure. The impact on humans is the same, but the one we are focusing on here is caused by input voltage to system.
Yes. And the compliance criteria for voltage flicker is based on the 2-hour flicker or long-term flicker. So it's a 2-hour value, 2-hour parameter, and that value is compared to a flicker value of 1 for 95% of the time. So your voltage flicker, your 2-hour value, is calculated from using 10-minute short-term flickers, and aggregated 2-hour needs to be below 1 per unit for 95% of the time. That's the compliant criteria for voltage flicker. Okay, so what can cause flicker, or how is flicker introduced or induced? So some types of loads can cause a rapid variation in your load current magnitude. Now this in turn causes a low frequency voltage variation superimposed on the amplitude of the voltage, and this will lead to incandescent lamps to flicker to the eye. Now some examples of loads that are common in introducing voltage flicker is waste pumps, ball mills, arc furnaces, and crushers are all loads that's common in introducing voltage flicker because of the rapid variation in the load current that it's drawing. So here's an example of a voltage flicker problem at a specific site. We can see the current, the blue line, compared to the line-to-line voltage, which is the red line. We can see the sudden increase in the RMS current at specific times, and that causes a rapid change in your voltage magnitude. So you can see the voltage magnitude dips, and that variation can lead to, or leads to voltage flicker. And we can see for this specific site, if we do an assessment over a longer period of time, we can see that the 95th percentile value, the maximum 95th percentile voltage flicker, long-term flicker, the green graph, is above the 1 per unit level that's specified in NRS 048. All right, and then in conclusion, it's very integral to assess in a power quality monitoring and management system, it's important to investigate voltage waveform quality. That's all the things that we've been discussing, the voltage regulation, voltage magnitude or voltage unbalance, voltage THD and harmonics, and flicker. Unmanaged and unmonitored power quality system can lead to serious health or safety risk. So it is important to have a power quality monitoring and management system in place. And the system is simple and it's cheap. It doesn't need to be expensive or hard to do. Now, VECTO 3 and Osprey Pro, what was formerly now called VECTO Grid OS, provides you with a very good solution and product that can give you the tools and the tools to effectively implement your power quality management system. It is developed to be implemented as part of your sustainable business process. So it was developed to be able to monthly or whenever you need to do assessments, to provide you with reports, to easily graph and plot the trends for you so that you can make this part of your system and your business operation. A power quality monitoring and management system will provide you with or optimize investment in, can help you with to optimize investment in equipment, can provide operational advantages, risk management, maintenance, assessment in when maintenance needs to be done, and support preventive maintenance and improved customer relations. So that's just some things that a very well managed system can help you as a business or as a company. Right, so that is now the end of the presentation. I think before we go over to demonstrating a report that we've generated from our system, can we take a few moments just to answer questions? I see Donnie, your hand's up.
Thank you, Hein. If you just go back to your voltage unbalance. I had an incident where, well, your voltage unbalance only refers to, just go either further back. It only refers to loads. Just one further back.
One further back. Yes.
You see, you refer only to loads causing voltage unbalance. I had an incident where the supply had an unbalance. Would it be correct to call that an voltage unbalance?
Yeah, no, definitely. It's also, this is just examples of loads that can cause voltage unbalance on the network. But if you are supplied on a system where there is inherently voltage unbalance caused by some other loads further up in the network, or the system just doesn't supply balanced voltages, then yes, it's also voltage unbalance.
Yeah, in this case, it was a solar farm, and one of the phases of the three-phase was lower than the rest.
Yeah, no, that is definitely also can also be defined as a voltage unbalance.
Okay. Then, yeah, sorry.
Sorry, Donnie, Randolph here. Just on that, although we focus here on the load, it's purely due to the principle common things occur commonly. So if you consider the likelihood of it happening on the generation end of things, a voltage unbalance from generator side is more likely to be picked up by a generator protection system and to be cleared quickly, whereas a load can sustain for a longer period of time.
Okay, just then on the voltage flicker, what I experienced from Richards Bay area, that the low fault level also aggravates your voltage flickering
Yes.
phenomenal. I just want to add that. Thank you.
Yeah, no, thank you, Donnie, for your inputs, and it's all valid, very valid points. It would be interesting to hear from anyone else that's also in the call if you've experienced, these and how you've experienced specific loads. But yeah, Donnie, just like you mentioned, on a low fault level, where there's a high impedance, that fast, rapid change in the current will definitely lead to a larger change in the voltage magnitude because of the impedance that's larger. So you would expect more voltage flicker issues than on other systems. Is there maybe someone else that you can share an example of one of these issues that you've had on site, or it would be very interested to hear.
Yeah, I can't share an example from this end, but what I'd like to just raise again is, Hein, in the closing slides, you mentioned the health and safety risk impacts that unmonitored and unmanaged power quality, specifically voltage waveform quality, can have. And that's something that all responsible persons and engineers on this session should really take to heart, where we typically look at the basic safety of electric circuits in the measure of insulation, overcurrent, over temperature, and so on. We often neglect the impact that something like a voltage flicker or sustained overvoltage can have on plant equipment, but also plant personnel. So if you are aware of a voltage flicker issue that could lead to someone with photosensitive epilepsy having a stroke or a seizure on your watch, that it is absolutely something you could have avoided or investigated in time. If you look at this specific slide, long-term measured flicker over 2 hours, that's not something you will see instantaneously, but an employee sitting at a desk for sustained periods of time exposed to this kind of flicker really has negative health impacts as well.
Yeah, no, definitely. Thanks, Randolph. Okay, while we busy with this, let's quickly go through a presentation or an example of a report that can be generated on Osprey Pro. I just want to stop this quickly, stop sharing, and then share the PDF. Okay, let me open up the report. Okay, Tebogo, can you confirm if you can see it?
Yes, I can see it.
Thank you. So here we have an example of a site assessment report that I pulled from our Osprey Pro system. You all are probably familiar with that. We also covered Osprey Pro, and there was 2 sessions specifically on that. So this was for a measurement point with the name Hawaiian Electric. It's a power plant for the period of 1 August to 1 September 2022. So it's a month period that we used the assessment. We can see that very important, as I said in the beginning, that the declared voltage here is set to 69,300, which is 5% above your nominal voltage, which is 66,000. So the voltage regulation will, and your percentages that's calculated will all be as a percentage of this declared voltage, 69,300, and not 66,000. All right, so firstly, we have a section where we look at the data availability. It's important to have a high data availability. So this will just make your data more valid, to make your assessment more valid. If you have a lot of missing information, there could be periods where you missed an incident or a specific issue. So flag data is just the percentage of data that are flagged, normally due to dips or swells. So if there was a 10-minute sample, in that 10-minute there was, for example, a dip, then that sample is removed from the assessment to not affect your power quality assessment. So 98.28% of the data in this month was captured and recorded and is used then for the assessment that I will show you next. So the first thing is the voltage magnitude compliance or voltage regulation. Here's the example of a good voltage regulation where we can see that the limits or the voltage regulation is well within the upper and lower limits. You can see the 95th percentile upper and lower limit, and then the 99th percentile upper and lower limit. And you can see that the regulation is all very stable and close to 100% of declared. So that's all well. If you look at the 10-minute readings, the actual readings and not the sliding assessment, you can see how your three phases change over time. And this is most likely impacted by daily loads that goes up and down. If you look at the histogram, we can also see it's well balanced. So your three phases are well balanced. And for most of the time, the highest peak, 15% of the time, it's close to 99.5% of the cleared. Right, and you can see that this band from its lowest value to its maximum value is small. So it's not, the variation in the voltage is not high, or not high. Yes. Here we just show you the loading, the load on the system, and that will obviously impact the voltage regulation as well. We can see there's two working points for this specific point we're measuring in terms of the load. There's a lower value, most likely during the evening, and then a higher value close to 10 MVA load during the day. And then we can see how the voltage profile looks generally over a 7-day window. All right, then we have voltage unbalance. Again, your highest 95th percentile voltage unbalance value, the 10-minute reading, was for this period is 0.3%, and that compared to the 2% compliant limit is well below it, so it's compliant. We can see looking at the 7-day sliding assessment that it is basically permanently low. So the voltage unbalance isn't an issue, and you can also just verify that by looking at the histogram of the voltage regulation, seeing that that is quite on top of each other, so very accurately regulated. All right. Is there someone?
Excuse me, go ha se wona. Umuntu bona ba go fane at least ho jana le number.
Oh, okay. We just muted everyone quickly. Okay, then we have voltage flicker. Voltage flicker that is compared to the assessment. So we can see for this specific point, because it's 66 kV, there isn't any limit specified in the NRS 048. So the assessed value was 0.5, but there's no compliance level that you can compare it with. And then it's your THD value, which is assessed as 1.7%, which is also well below the 4% level. You can see how your THD, the 10-minute values change over time, over this month period. You can see there was an increase in the THD at that point. And then you can also compare that with your current THD as well. But the voltage THD is used for the assessment. Here we can see how it changes over time, and then, or a typical week. And then lastly, okay, this is a voltage events. This is for dips. It shows you the dips that it had during this period. There was 5 Y dips, 1 X2 dip, and 5 interruptions. You can see, looking at the dots, when in time that dips happen or interruptions happen, and how it affected your compared to your voltage regulation. And you can, here's the scatter plot, the NRS 048-2-2015 scatter plot, just to to classify the dips. You can see there's the 5 Y dips, and then the 1 X2 dip that most likely can cause equipment to trip or plants to lead to plant failure or plant shutdown for short periods. So that would be an important one to investigate, for example. It shows you when in time, maybe statistical graphs that show you what hours of the day the events happen, to see if you see any specific pattern, and then in terms of what day of the week. So over a long period of time, this data becomes very valuable to assess if there's specific trends that you recognize, maybe seasonal trends or hourly trends, and so on. And then lastly, it's the voltage harmonics that's compared to your limits. So this is for HV network, and we see the individual voltage harmonics is all compliant and also below the compatibility level. All right, I think that summarizes the report. This report can be generated in a Word format as well, so you can, all of these graphs can be copied and pasted over into your own document. And then lastly, what I want to add, a new report that we've discussed, I think in the first session of this training, that we're doing. So in the power quality standards session, we mentioned quickly that you also have the ability to specify individual harmonics for specific sites. This is more applicable to IPPs or renewable power plants where they have specific limits according to their contracts. It's not a compliance report, so it's not a full compliance report, but it gives you a report with an indication of how your power quality compares to the limits of that site, not compared to the NRS limits. So that's also something that you can do in Osprey Pro and specify for every measurement point. All right, I think we are quite a long, it's only an hour into the session, so we have a lot of time left. Can I ask if there's any more questions, anything specific that you want to focus on or want us to look at? If not, then I thank you for joining the session as well. Donnie, I see your hand up again.
In that report, on the last page, I saw a triplen harmonics. What does that refer to?
So, Donnie, triplen harmonics are multiples of the third. So the reason why triplen harmonics gets special mention is that in delta connections of transformers, triplens are mitigated because there's no neutral path for them to return on. The full list of triplen harmonics actually includes, 3, 9, 15, 21. So they are special harmonics because in some situations you expect them to never be present, and it also goes as an indicator for your neutral earthing strategies.
Yeah, I was used to the third harmonic, but not the triplen harmonic. It's a new terminology. Thank you.
Okay.
You're never too old to learn.
Yeah, so the only reason why we're not showing the other harmonics is because is at this voltage level, there isn't any limit specified or level specified for those harmonics. So we only show the ones that there is actually limits for. But you can on Osprey Pro do a harmonic spectrum graph that shows you the other harmonics as well.
I believe there was another hand raised. Was it Carl from Eskom?
We can just see Carl, yes.
That's correct, yes, sir. Thank you. Just want to check with you, is there a way to filter out time-based analysis of, let's say, the harmonics so that one can then start filtering between what was attributed by PV and maybe by the PV or the inverters during the night times and so on? Is there that ability to do that?
So if I, sorry?
The trend, will it trend over time? So there's, Carl, I think the short answer is there's no quick way to do it, but all the data required is available as a CSV export. So you could do a 10-minute trend or a 3-second trend or whatever you've enabled on your vector. And then you could pull for the specific harmonics you're interested in. From the export, you just mask it over the time when it's sunshine out.
Okay, thank you.
I'm not
Just
sure,
a last.
does that answer your question, Carl? I'm not sure exactly. I understand what you mean, but there's not a report that you can do that. You can, however, plot the trends for specific periods to look at the values during that period, but it's not going to tell you if it's contributed by the plant or from the network.
So, Carl, just a very, very important thing to note here. We touched on it or Hein touched on it in his slides, that harmonics have phase angles as well. And that you could perhaps, by looking at the prevailing phases, a method that was developed within ESCOM by Brandon, by using that method, you could look at the phase angle of the specific harmonics of interest during daytime and nighttime, if there is that phase shift attributable.
Okay, thank you. Just the last one. How far can you go with your software and your equipment with regards to harmonics? What is the limitation? Are there limitations?
So we can, in terms of harmonic spectrum, we can measure up to 25 kilohertz, which is because we sample at a very high switching frequency of 50 kilohertz. So the individual harmonic components can be plotted up to the 63rd harmonic. So that's also higher than what the NRS specifies or normally specified in the IEC, 61,000. But then we also have another functionality to plot up to 25 kilohertz in 200 hertz bands. So we plot bands of 200 hertz up to 25 kilohertz. That is also defined how it's done in the IEC. But we can also take the step further and actually trigger a waveform recording that you can then use to do an FFT on. And that FFT, a fast Fourier transform, will then give you the exact harmonic spectrum or plot up to 25 kilohertz as well, not just in 200 hertz bands. So you'll then be able to see harmonics jump out at higher frequencies, for example, and so on. But it's very important to note at this point that even though the device, the Power Vector 3, can measure that, you still need to measure on or use a VT or a CT that can provide you with that broadband accuracy. And that is sometimes the issue with doing compliance assessment studies, is that there's a high uncertainty when you get above 1.5 or 2 kilohertz on the accuracy of that individual harmonic, because you just don't have that that broadband accuracy from the VT that you're measuring on. And that's why we actually, my colleague last Friday presented at the AMEU a very nice presentation that we can most likely share with you as well on low power VTs. That is what we see the enabler to provide you with a method to accurately record voltage and also current using low power instrument transformers to get a broadband accuracy on harmonics. And then in conjunction with the Vector 3, you can measure that very accurately. Randolph, do you want to add?
Yeah, just to mention there, although we're sampling at 50 kilohertz and we give you access to high quality visuals up to 25 kilohertz, like Heinz said, anything above, say, 3 kilohertz, your conventional magnetic voltage transformer will filter out a lot of the quality information available. And specifically also, it has resonant points in the higher frequencies. So you wouldn't be certain if the higher content is attributable to the measurement transformer you're using or actually by the load or generator that you're investigating. On the low power VT side of things, we are reading about broadband up to 30 kilohertz high accuracy sensors. So it's definitely a technology to be used in conjunction with a VECTO 3 to get higher quality analysis out in the field.
Yeah, agreed. I could see at my house on the 300th harmonic actually it starts so that my inverter starts singing to me. So it was quite interesting to see. But yeah, I'm just curious if you guys have ever seen it on a bigger scale wise, especially these high voltage, high switching frequency inverters, what those higher frequencies are going to start doing to the networks would be interesting to see.
Yeah, no, Carl, we actually have a few examples of that, and we recently were involved in a study at a specific site. It was a solar PV site as well, where we measured at the inverter output terminals or on the LV terminals of the transformer, and I can just tell you that the readings that we recorded in terms of the current waveforms it will actually blow you away when you see the harmonics that's actually being generated at a higher frequency. And I think the thing is that will impact your transformer, can lead to transformer overheating, gassing, and failure over time. So that's definitely an issue and something that I think needs a lot more light. And to really accurately analyze that, you need a VECTO 3 or a Class A recorder, but also then something like a broadband VT and CT so that you can get that accuracy.
Another interesting thing that we've seen is conventionally, if your inverter manufacturer lumps as part of its supply the step-up transformer and the MV switchgear, oftentimes on a skid or containerized, it's almost of no consequence to you what happens on the LV side of the transformer. But what we're seeing in the South African market is a drive towards local content, where the solar EPCs go and they say, okay, we'll purchase the inverter from an OEM, we'll purchase the transformer from another OEM, and we'll purchase the switchgear from someone else. And then you're setting yourself up for a fight when it comes down to the scope and the risk and limitations, because the inverter manufacturer that typically lumped the transformer with his supply is open to take the risk of the inverter harmonic emissions onto his transformer. But the moment when your transformer manufacturer and the inverter manufacturer are different parties, then each one of them needs the most amount of information available to ensure that they can actually guarantee you the 20 or the 25-year lifetime that the equipment's supposed to last.
Agreed. I think they are, on our transformer sections, they are busy working on that for especially ECCGs and our large power transformers as well, to look at that currently.
So with regards to the bandwidth, Carl, just to add on there, obviously the bandwidth is only an issue once you look at the higher voltages. Our device is perfectly capable of measuring on the LV side of things at the full bandwidth that we mentioned on our data sheets. So it's just about what sensors or transducers are you connecting to make sure that the information that gets to the device is not filtered by some means.
Yeah, so if you ever do compliance assessments, it just needs to take that into account. Specifically, this becomes an issue with IPPs where they need to provide compliance, and that's up to the 50th harmonic. So there's definitely an uncertainty the moment you start looking at the higher harmonics, even below the 50th harmonic. So yeah. Do we have any other comments or questions? Ronald, yes.
Sorry, I see that we have on the call today some people with some intricate knowledge from the solar EPCs and some battery experience as well. I don't know if one of the two Johans from Solar F would like to contribute any of their findings on battery energy storage system, power quality, or solar PV power quality. One of the two Johannes, if you would give us the privilege.
Not both of us at the same time, please. Yeah, I must apologize. I did join late, but I am following as much as possible. What I can comment just as a broad statement with regards to energy storage is I'm expecting it to become very interesting because there's two different scenarios. If you grid tied with your energy storage, as in an arbitrage system or a peak shaving system, you're synchronized to the grid in the same way you would be with grid tied PV. So I would expect similar behavior. However, when you switch to an islanded operation, so you're going from a current source to a voltage source operation, I expect the harmonic spectrum to change. And it's something that we try to measure with power quality meters. But not something that we analyze and sift through as frequently as we might want to. So there's some homework there still to be done.
Thanks for that, Johan. I'd also just like to hear your opinion on an often overseen fact that if you are doing microgrid design with battery storage inverters, that oftentimes the consultants just look at the energy and say, okay, this is great. We need this plus round trip efficiency. So that's the amount of storage we need. Yet at the higher harmonics, your battery inverter still needs to create everything that your load can possibly ask from it. So if you have distorted or nonlinear loads, oftentimes the lump sum energy look at things is not giving you the true reflection of the capability that your equipment needs.
That's a very interesting point, and something I'm definitely going to think about in the shower later. Yeah, that I can imagine that to a small extent, but that would influence the amount of kilowatt hours that you need to provide.
Thanks. Thanks, Johan. Yeah, floor is open to anyone else willing to contribute experience or insights from different sectors as well. I see we have a lot of Eskom employees on the call today. We have quite some good representation from the municipalities as well.
Silence. All right, no, thank you guys. Then if there's no other comments or questions, I thank you for joining the session today. And if you have anything else that you can think of later, you're welcome to send it to us via email, give us a call. We're welcome to assist you with that. And please share the future sessions that we will be doing. We will announce the dates and the topics of the future sessions, hopefully in the near future. And yeah, let's make this. I think there's definitely a need in South Africa for power quality group and discussions more like this, where we can discuss industry problems and all learn from each other. This is becoming more and more interesting as the network are evolving and with everything happening internationally. So I think there's a lot of info that can be shared, and we can all learn from each other. If there's also topics that you would like for us to discuss specifically, if it's with regards to a specific feature on Osprey Pro, or in terms of the VECTO 3, you're more than welcome to contact us, and we can see if we can make that available or do that as well. So yeah, from my side, I thank you. Thank you for Randall for your contributions as well. Anything to add from Daniel Tabogo?
Okay, from my side, I just want to thank everyone for attending. Thank you very much for your time. And I just only need 3 email addresses. There are 3 attendees that I don't have their email addresses, because after the meeting, normally we send the recordings and all other stuff. So I'm going to need the email addresses. Selaelo, Leslie N, and Carol. Can you please, maybe in the comment section, send your email addresses so that Danielle can have them on record? Danielle, do you have anything to say?
Nothing from my side. Thank you for presenting, Hein.
Okay, thank you everyone for attending. Thank you, Hein, for the presentation, and Randolph, thank you very much for your contribution. We will send you the details of the next training, and thank you again. Goodbye.
Thank you, everyone. Goodbye.
Thanks, everyone.
Thank you. Bye-bye.
Thank you.
Thanks, everyone. Bye.
Thanks, everyone. Bye-bye.